So we're trying to look at quantum physics and the different pieces that make up the jigsaw of quantum physics. In the previous lecture, we discussed quantum erasure and delayed choice. We also looked at a gravitational lensing experiment, and just a quick recap of the final point that we were discussing the other day. We have a big galaxy and a light source, and this is our Earth. So if a single photon comes from this light source, it bends by the gravitational lensing effect. And on Earth, we can choose to detect this single photon in two particular fashions. First of all, we could have a screen with two slits in it. And in this case, we would see an interference pattern for the single photon. The other possibility is that we were to make a choice of using two telescopic detectors to look at the photon, and these detectors are pointing in different directions. So in this case, no interference would be observed. Sometimes a photon is going to be registered at this telescope, and at others it's going to be registered at this telescope. Here a photon does show single photon interference. Idhar tawajjuh kar lein, excuse me, started our lecture. So now this photon has taken billions of light years to reach Earth, and our choice of observing this single photon through two different kinds of detection mechanisms determines what kind of outputs we see. In this case, we see the interference of a single photon, and we make a choice of whether we would like to see this interference pattern long after the photon has emerged from the region where interference could have taken place. So it's a delayed choice experiment. Yes, please.
Sir, isn't it the case that even in the experiment where we are using two telescopic detectors, interference is still happening, but we are only detecting it where constructive interference?
Well, you can use an array of telescopes. Use an array of telescopes. Instead of using two telescopes, use a complete array of telescopes. No. All right, so this is where we've finished off our lecture. This is delayed choice. And I've uploaded some really nice material which describes the delayed choice quantum erasure experiment. So let's today shift our attention to a little bit of more mathematical mechanics, which helps us look at different facets of quantum physics. And all of this is for a purpose. With this machinery that I'm going to introduce today, which of course is built upon the machinery of Kertz and Braz, we'll be able to understand to some extent quantum computing. We'll be able to understand quantum communication, quantum non-locality, and quantum entanglement. So this kind of orientation is going to open up the floodgates of the quantum revolution into your minds, hopefully so. So let's talk a little bit about representing quantum states. So far we've seen that we would like to represent quantum states by some label, say psi, and put this inside a ket. This is our quantum state, no matter what the physical manifestation is. And we also saw that in order to describe this state, it's customary to resolve this into a particular basis, some coefficient here and some coefficient here. Ket 0 and ket 1 form a basis. Ket 0 and ket 1 are a basis. Any quantum state which is a qubit can be represented as a superposition of these basis states. A and B, we all know, are complex numbers, and there is certain constraint on their modulus. Now, an alternative representation of quantum states is by representing this quantum state in terms of a vector. And what do I mean by a vector? I mean a column vector. Now, when you want to do analysis on a computer, for example, or you would like to see how quantum states change with time, or what's the impact of different kinds of elements on quantum states, as we saw in an interferometer, a quantum state comes in, you have a beam splitter, you have a mirror, then you have detectors. So something is happening to quantum states in a quantum process. So how do we kind of encode this on a computer, or if we had more complicated states and more complicated processes, how do we kind of look at the progression of quantum states, and luckily how do we encode all of this onto a computer? For this, it's customary to represent a quantum state in terms of a vector, and more precisely a column vector. So what we generally do is we represent a quantum state psi by a column vector. Since it's a two-dimensional quantum state, because the Hilbert space is two-dimensional, there are two basis states, therefore this column vector has two entries. It has two rows and just one column, that's why it's a column vector. Now, how do we represent this particular quantum state, for example? For this, we need to come up with a definition of what do the basis states look like in this representation. So we define, this is a definition we make, or a particular choice of basis quantum states. So what we do is that we represent the quantum state get 0 by a column vector, which has 1 at the top element and 0 at the bottom element. This is our vectorial representation of ket 0, and the vectorial representation of ket 1 would look like this. Put a 0 on the first position and 1 on the bottom position. So this is how you would represent the two basis states. This is our definition. So whenever we do a calculation, we always define what the basis states look like in this representation, and unless stated otherwise in quizzes, homeworks, in class, we'll stick to this definition. All right. Now, in this definition is really useful, as I'm going to elaborate in a minute. But with this definition, if I were to take ket psi, I know that it has A of ket 0 and B of ket 1. And A and B are not the amounts of 0 and 1, they are really probability amplitudes. Just keep that in mind. They are complex numbers, kind of magical numbers that do not make sense on their own, but they make sense when you take the modulus square. So if we make this definition for the representation, what kind of representation would the state psi have? It would have an A here and a B here. That's it. All right, because this really is A times, which is a scalar, ket 1 0 plus B times ket 1. So if you just compress all of this together, this is what state psi looks like. Yes, please.
Sir, if we make a bracket of ket 0 with itself.
I'm just going to come to brackets in a minute. So right now we're talking about kets. This is what a quantum state is represented like vectorially. For example, if I have a state, say my psi is 1 over under root 3 ket 0 plus ei pi by 6, 2 over under root 3 ket 1, its representation with this definition is going to be 1 over under root 3 on the top position and 2 over under root 3 ei pi by 6 as the second element. This is how you would represent this particular quantum state in vectorial notation. This is a real column vector, the kind of vectors and matrices that you are accustomed to. Got it? So these entries, by the way, can be complex numbers. Now let's talk about bras. So we've defined or represented quantum states. Now we would like to shift our attention to bras. Now what a bra is also a vector, but it's now a row vector. So if my ket is a column vector, my bra is a row vector. And I can come up with a similar definition for bras, and that definition just stems from the definition that we have for kets. So if this is how I represent my basis kets, my basis bras would look like the following. Bra 0 is this row vector 1 0. My bra 1 is this row vector. All right. So with this definition, if I were to choose this quantum state with a column representation, vector representation A and B, my corresponding bra would look like a row vector with two entries. The first entry would be A, the second entry would be B, but now I would like to take the complex conjugate of A and the complex conjugate of B, because as you know already that if I were to choose that quantum state over there, this is really equal to A star, the complex conjugate of A bra 0 plus B complex conjugate of B and the bra associated with ket 1. So this is how this bra is going to be represented in vectorial notation. Now why is this useful? This is useful because suppose I have two vectors psi given by A 0 plus B ket 1. I have another vector, let's call it phi. Let's represent this as C ket 0 plus D ket 1. Now how do I find the inner product between these vectors, which is the overlap of one quantum state with the other? I form the inner product. So I convert one of these numbers in one of these quantum states into the corresponding bra. So suppose I have to calculate this inner product now, bra phi ket psi. So one way is to kind of write this down in bra ket notation and do the multiplication. And the other way is to use our vector. So let's first do this explicitly. So my bra phi is going to be the bra of this term C star bra 0 plus D star bra 1, and then I juxtapose this or write this with this ket over here, A ket 0 plus B ket 1, and then I do the point by point inner product. The inner product of 0 with 0 is 1, 0 with 1 just vanishes. The inner product of 1 with 0 vanishes, 1 with 1 survives. So I'm left with C star A plus D star B. This again is a new complex number. Now let's do all of this in our vectorial notation. For the bra phi, I could write the row vector C star D star, and for the ket psi, I can write the column vector AB. Now I have a row vector being multiplied with the column vector, and both of these vectors are compatible for multiplication. You know how to multiply vectors, right, and matrices. So this turns out to be C star A plus D star B. All right, so you could either use this explicit kind of formulation of writing your kets and bras in terms of basis vectors, or you could use the vectorial notation of using row vectors and column vectors. Either of these works. Now the question that some student asked is, what's the inner product of a vector with itself? Suppose my vector is A ket 0 plus B ket 1. This inner product is simply going to be this row vector multiplied by the column vector. This turns out to be A mod square plus B mod square, which is equal to 1 because the vector is normalized. So now we have an alternative representation of kets and bras in vectorial notation. Now once you have this vectorial notation available to us, you can code all of this on a computer, on a classical computer, and do calculations. So the inner product is just a row vector being multiplied by a column vector. Yes, please.
Is it a rule of thumb कि जब भी हम row vector लिखेंगे तो हम A conjugate लिखेंगे? We cannot write A when we need to.
So you just, so if you have, this is your vector over here. This is your quantum states are synonymous with vectors. So if this is your ket or your quantum state or your vector, the corresponding dual to this vector is going to be a bra. It's going to be a row vector, and you take the complex conjugate of these terms. Now all of the column vectors that you can find in the two-dimensional space, they live in that two-dimensional space. So the quantum space is the space of column vectors, and the dual space that we hinted at in one of the earlier lectures is the space of all the row vectors. So all the row vectors also form a vector space, and that is called the dual space or the bra space. Now this is a really nice representation of kets and their bras because it's really brings home the ideas of simple matrix multiplication, and you can code all of this onto a computer. Now so it's really easy to work with either kets, bras, and use their kind of formulation in the ket and bra space, or convert them into vectors, column vectors or row vectors. Any questions? Probabilities now. Any probability, for example, suppose I have a quantum state psi coming into a measurement device, some measurement device. This could be a photon with polarization, the path of a photon, the spin of an electron, the current through a superconducting quantum interference device, the flux in a squid. It could be anything. Now this measurement device has two output channels, one corresponding to ket 0 and the other corresponding to ket 1. Now we already know that the probability that this channel gets an output, let's call it P0, is given by the inner product of the state that you feed into this measurement device with the quantum state that corresponds to this channel. Then you take the modulus square. Now this also has a vectorial representation, because we know that inner products have vectorial representations. So you can use either the vector notation or the explicit formulation in ket and bras to find out probabilities. So everything is now tied together in a seamless whole. Now is the time to really talk a little bit about composite systems. Since we've already seen in our discussion of quantum erasure that two degrees of freedom can combine with one another. So how does this vectorial notation carry over to composite systems? Now for example, I have a quantum system ket psi, and I talk about another degree of freedom. So I form this composite space. So this could be for example, this could be the path of a photon, this could be the polarization of a photon, this could be a photon, this could be an electron, these could be two different properties of electrons. All right. So now in this particular case, how do you represent this in vectorial form? That's the question. Do you understand the basic concept of what do I mean by a composite system? Or do you want me to re-explain? Okay, I can re-explain. Suppose I have my interferometer and then I place polarizing elements in the paths of this photon. So now I'm not only concerned just with the path that a photon might take, I'm also concerned with its polarization. So let's look at the input port, the input photon. The input photon is coming in the path ket 0. So I define its path quantum state with ket 0, but I also need to talk about its polarization, because now polarization is becoming important in this experiment, because I have elements inside this experiment where I have placed elements that can transform the polarization. So this system is not immune to polarization any longer. It affects polarization. So I need to define two properties of this photon, 2 degrees of freedom. One is the path, the other is the polarization. Each one of them is a quantum property. So I define a quantum state corresponding to the path, and I define a quantum state corresponding to the polarization. What's the polarization here? Horizontal, vertical, anything else? If this represents my optic axis of the polarizer, this is a horizontally polarized photon. So as far as its polarization is concerned, it's in the ket H state. And now what I could do is I can put this symbol in between path and polarization. This becomes a bigger quantum system. This is an example of a composite quantum system which has 2 subcomponents to it. One is the path, the other is the polarization. And you want to do something useful with quantum physics, you need to have big systems. Otherwise, single qubits are not really good. They're good for learning purposes, but they don't do anything useful. So you need really big quantum system, and that's why quantum computing is so difficult, because in order to make it useful and in order to make quantum computers supplant or replace classical computers, you really need them to be big. For example, people say that you need to have at least 100 qubits. So you need big systems. So you need to combine different elements together to form these composite states. So if I were to talk about each, now is this a qubit? Is the photon path a qubit? Is the polarization a qubit? How many basis states does just the path have? 2. And the polarization? 2. So overall this composite system will have 2 times 2, which is 4 basis states. Now how do we represent those basis states? So now I understand that my first location in this tensor product or direct product, first location corresponds to path and this corresponds to polarization. Now I always keep that in my mind. So this is a space corresponding to the path degree of freedom, and this is a space, a vector space corresponding to the other degree of freedom. So just always keep that in my mind. Ordering of these labels is important, that is. So the path could be ket 0 and the polarization could be ket H, right? So this is one basis state for the 4-dimensional system now. Now I have a 4-dimensional system because I've joined 2 qubits together. So this is one possible basis state. The other possible basis state is correct. A third possible basis state is all right, and the fourth basis state could be ket 1 crossed with ket V. So this is a nice choice of the 4 basis states, isn't it? Now it becomes cumbersome for a teacher like me to keep on writing these dot products, these tensor products again and again. So just for convenience, I could also write this as ket 0, ket h. This is just for convenience. So all right, this is just notational convenience. And sometimes if I feel more lethargic, I can write this as 0h, 0v, 1h, 1v. All right, and even feel more lethargic. So there is no limit to lethargy. I can just replace the h and v, so I can call h as 0 as well and v as 0, 1. So I can write this as 0, 0, 0, 1, 1, 0, 1, 1. So just remembering that the first label corresponds to path and the second label corresponds to polarization. Correct? Got it? Now this sequence of 4 binary digits 0, 0, 0, 1, 1, 0, 1, 1 is very similar to what you see in digital logic design or computer networks. So you have 2 bits. If you have 2 bits, 4 possibilities exist for the state of those bits. Now this is our quantum state, our composite quantum state. Now how do we represent any one of them in vectorial notation? Let's focus our attention, say, on this particular state. Or let's do all of them one by one. This particular state is really this state, ket 0 tensor product with ket 0. This is our definition for representing vectors. So what I need to do is I need to find the tensor product of these vectors. All right, that's what I need to do. For this I need to do the following: 1, 0, tensor product 0, 1, 0, 1, tensor product 1, 0, 0, 1, tensor product 0, 1. All right, got it? So how do I find out, how do I do tensor products? This is a simple task in linear algebra. So I'm going to write down the tensor products here at the bottom. So this is state 1, state 2, state 3, state 4. So the first kind of tensor product, what I need to do is, all of this by the way can be coded on a computer. That's the utility of this representation. I take the first element 1 and multiply it element by element with all the elements of the second vector. So take 1, multiply with 1, then 0 with 0. So I do this multiplication followed by this multiplication. So the result would be 1, 0, 0, 0. This is my state ket 0, ket 0 in vector notation. Ket 0, 1 is going to look like, I take this 1 and multiply it throughout and then multiply 0 with all the elements. I will get 0, 1, 0, 0. 1, 0 is going to look like 0, 0, 1, 0. And my ket 1, 1 is going to look like, all right. So this is the representation of all the 4 basis states that now span the 4-dimensional composite quantum system. By the way, if I were to choose any 2 of these column vectors and I form the inner product, which is like forming the dot product, what would the answer look like? 0. Which means that all 4 of these column vectors are orthogonal. So not only are the quantum states orthogonal in the quantum sense, but the vectors that are used to identify the quantum states, They are also orthogonal in the linear algebra sense. So two vectors are orthogonal, as you recall, when their dot product is 0. And how do you find the dot product? You just take this to be a column vector, this is a row vector. You find the transpose of column vectors, you get row vectors, and then you do an explicit multiplication. Yes, you had a question.
So is tensor product applicable on matrices as well?
Sorry?
Tensor product is applicable on matrices as well.
Yes.
So how do we calculate the dimension of this application?
So if this is these are two column vectors, so you just take the size of the basis of this, which is two elements, you get 4. You have a third qubit, you'll get 8. You'll have 4, you'll get 16, and so on. Any questions? So far, so good. So now if I have a 4-dimensional quantum system, 4-dimensional quantum system, which can be made from two qubits together interacting with one another form a 4-dimensional space. Now that 4-dimensional space is spanned by these 4 basis vectors over here. Now there are two ways of making 4-dimensional spaces. Either take two qubits and correlate them together, or you can have 4 levels to start off with in a new system which is not a qubit. But alright, so let's forget about that for a minute. Now I have a 4-dimensional quantum state. Now if I were to represent this 4-dimensional quantum state, I need 4 basis vectors, correct? So the 4 basis vectors are 0 0 plus 0 1 plus ket 1 0 plus ket 1 1, and I need to write 4 complex numbers with each of these terms, right? So I can write, let's call this C0, C1, C2, C3. Each of these C's is a complex number. And is there any constraint on these C's? What's the constraint on these C's? Add hoke nahi, modulus square hoke add hoke 1. So the constraint is that I add up all of these numbers after modulus squaring, I should get 1. So this is the normalization constraint. Got it? Now in this representation, when we have defined this to be our 4 basis vectors and we have defined this to be our representation, I can represent this quantum state as a column vector. Now what would be the 4 elements of that column vector? Nah. So what do I write in the first position? C0, C1. So this is the vectorial representation of this 4-dimensional space. Likewise, if I were to form the bra for this would now become a row vector, a long row vector. I just take the transpose of this column vector and find out the complex conjugate of each complex number and put it in. And you can readily check that if I were to take the inner product of the vector with itself, which means multiplying this row vector with this column vector, this condition will automatically pop out. This is how I represent 2-dimensional spaces, I represent 4-dimensional spaces, I represent composite systems, and so on. So this is how we talk about quantum states. But in our beam splitter experiments, there are two elements to the story. There are two characters in the plot. One character are the quantum states. And if you see this process, this circuit, this looks like a circuit. A quantum state comes in and it propagates through the experiment, the process, and some quantum state is output. That's what you normally do in a computer or an information processor of any kind. That's what the universe does. You have an input state, some kind of input quantum state, could be a single qubit, could be many qubits, and you get some kind of output, psi out. And in between is your process, your quantum process. Here our process is an interferometer. And you look at the progression of the quantum state through this process. So there are two elements to the plot. One are the quantum states. What is the second element that we need to pay attention to? Mechanical? Or what's happening to the quantum state? The quantum state changes as it propagates through the process. Now there's some element that changes the quantum state. This beam splitter has a transformation. It transforms an input quantum state and creates output states. The mirrors do a transformation. Empty space through which the photon propagates is a process. The process is doing nothing. So there are quantum states and there are transformations on the quantum states. Transformation means you do something to a quantum state to generate an output. So each of these elements does something to quantum states. Now let's be a bit more physical and let's talk about this interferometer, because by now you're already very familiar with interferometers. So what are the two different kinds of elements in that Mach-Zehnder interferometer? That's right. So there's a beam splitter, there's a polarizer, and there's a mirror. Now polarizers are slightly difficult, but let's start just with beam splitters and mirrors. Let's first of all look at mirrors. My friend, are you getting me? Thinking about something else, or is it making sense? So let's look at a mirror. Now we defined the kind of transformation a mirror does in our previous lectures. What does a mirror do? It converts ket 0 to ket 1 and ket 1 to ket 0. So if I were to make, so how do I represent this? So this is a mirror. What a mirror does, it takes ket 0 and converts it to ket 1. It takes ket 1 and converts it to ket 0. This is the action of a mirror. Action in quantum states, you generally call this to be a transformation. So this is a transformation that a mirror achieves. Now what's happening here, if I were to look at the vector representation of ket 0, ket 1, ket 1, ket 0, what's happening is, what the mirror does is it takes the state which is represented by this column vector and converts this to ket 1, which is represented as 0, 1 bottom place, correct? And it takes this input ket 1 and converts it to ket 1, 0. Now what we would like to do, if quantum states are represented by vectors, can you come up with a kind of object, whether it's a vector or a matrix, that can achieve a transformation of states?
Yes.
Yeah. What is the meaning of yes?
A matrix.
So we need a matrix that does a transformation. So what we really need to do is, if I were to have a quantum state psi, I can write a matrix for the mirror. Let's call such a matrix U, right? Let's put a small mirror with this. So this is a matrix that represents a mirror. And it's customary that when you talk about quantum physics, when you deal with matrices, you put a small hat on it. All right? Why do you put a small hat on it? Because these matrices are called operators. So this operator acts on a quantum state to give you a new quantum state. Psi out. So every quantum process is really some matrix, some operator, takes in an input state and churns out an output state. Now if I were to look at the transformation a matrix achieves, a mirror achieves, what kind of matrix do I need to write? What would be the matrix corresponding to this transformation? So let's first look at the identity matrix. Suppose my matrix, some matrix is identity. What does this matrix do to any quantum state? It doesn't change it whatsoever. So if you're doing nothing, if a quantum state is doing nothing, then the transformation corresponding to that do nothing is the identity matrix. Do nothing. By the way, doing nothing for human beings is also really, really hard. And that's called meditation. Muraqabah. It's really hard. And in quantum physics, doing nothing is the hardest thing to do, because quantum states are so fragile and frail that they immediately interact with the environment and they change. So preserving a quantum state for long periods of time or over long distances is really hard. So this is a matrix that corresponds to do nothing, unit matrix. Now let's talk about the operator that corresponds to a mirror. Now what does the mirror do? Let's talk just about the basis states. What does a mirror do to the basis states? It swaps them. It converts ket 0 to ket 1 and ket 1 to ket 0. So what kind of matrix is needed that achieves this? So what do I write here? 0. Beautiful. So if I were to take this matrix and act on this input state, I would get this state. For example, excuse me, no talking please. U mirror acting on ket 0. What should my answer be? Just forget about the vector notation. Ket 1. I should get ket 1. Correct? Now let's see if this definition is making sense. So I write 0, 1, 1, 0. Ket 0 is represented in this fashion, and my output is going to be, I do now a brute force multiplication of matrices, something that you're really, really familiar with. 0 multiplied by 1, nothing. 1 multiplied by 0, nothing. 1 multiplied by 1, and that's right. So this indeed is ket 1. And I can check it with the other basis state. So you just need to check with the two basis states, and everything else will follow. Everything else is going to follow. So this is the matrix or transformation corresponding to a mirror. By the way, those who deal with computer circuits or digital logic, Is this transformation here similar to some kind of logic gate? What kind of logic gate is it? It's a NOT gate. So if you have quantum mechanics and you have quantum objects, you're dealing with single photons, then this matrix represents a quantum NOT gate. All right, which means that now it's trying to inch closer and closer towards quantum computers and quantum information processors. I can draw a circuit for this. The circuit looks like a wire which carries a quantum state psi, and now I have a U that corresponds to the NOT gate, which is this gate over here, and my output is U0 acting on my input state. If cat 0 comes in, cat 1 goes out. If cat 1 comes in, cat 0 goes out. If an equal superposition comes in, suppose my input is this equal superposition of cat 0, and what is my output going to look like? It's just the same. It's just the same. So if this feeds into a NOT gate or this matrix, nothing gets out. So let's check this vectorially. My NOT gate is 0, 1, 1, 0. What's the vector representation of this quantum state? Of course, it's going to be a column vector. But what should I write in the two elements? Please, aap bataएं. Right. So I need to put in 1 by under root 2, 1 by under root 2. Let's see what my output is. 0 multiplied by this is nothing. This gives me 1 by under root 2. This gives me 1 by under root 2. So I get the input back. So if I feed in an equal superposition to this quantum NOT gate, I get the same state back. But this is only for this special input state. What a NOT gate generally does is it does this to an input state. Can you now write off the tip of your sleeves the operator for a beam splitter? Remember what a beam splitter does? Cat 0 is converted to cat 0 plus 1 over under root 2, and cat 1 is converted to cat 0 minus 1 over under root 2. So what would this operator look like in vector form? So I just put 1 over under root 2 outside, factor it out. So what do I write? 1. This is the matrix for a beam splitter. All right. Now there's an easy way, really easy way to write down matrices of this kind. The easy way is you look at the first column. The first column represents the output when you feed in the first basis state. The second column represents the output when you feed in the second basis state. Let's look at this NOT gate over here. When you feed it in with the first basis state, which is this state, the output is 0, 1. So put 0, 1 in the first column. When you feed in the second basis state, which is cat 1, which is really 0 here and 1 here, the output is cat 0, which is a 1 here and a 0 here. That you just write in the second column position. So this is an easy way of constructing these transformative matrices. By the way, if this is what a NOT gate, gates of this kind, now beam splitter is a physical device, but these gates are common. So when you implement quantum information processors, you might not be dealing with photons, you might be dealing with superconductors or some other kinds of devices. So this gate, by the way, This is also a quantum gate. This is called a Hadamard gate. Hadamard. Because Hadamard was the name of a mathematician, and matrices in which each column vector, all the column vectors are orthogonal to one another and all the row vectors are orthogonal to one another is called a Hadamard matrix. So that's why this kind of gate is called a Hadamard gate. Now before we take a break, I have a small problem for you. Can you verify if you were to take this beam splitter and feed in the superposition state, what should your output be? We've already seen this when we look at the progression of quantum states. What is the output when you feed in the superposition state into a beam splitter? Get 0. Now can you verify this please? Using the matrix notation that we've introduced. Please verify. Right. अब इसको मल्टीप्लाई करो. कर दी मल्टीप्लाई. So the answer should be a vector, not a matrix. So when you multiply a matrix with a vector, the answer is another vector. It's not a matrix. Just look at the rules of multiplying matrices with one another. हाँ करो ना मल्टीप्लाई इसको करो. अब करो, ठीक कर रही हो. ठीक है, लेकिन मैट्रिक्स मल्टीप्लिकेशन से भी करो ना. कर लिया अपनी मैट्रिक्स मल्टीप्लिकेशन से भी करो. मैं आपको करके all right. So let's write down the matrix for this beam splitter. Excuse me. The matrix is 1 over under root 2, 1, 1, 1 minus 1. This is the beam splitter or the Hadamard matrix, and this is an operator that acts on an operand. The operand is a quantum state. The quantum state that we are focusing on is this quantum state, 1 over under root 2, 1, 1. The operator is like a predator. The predator preys upon a quantum state to give a new quantum state. So now if you were to do this explicit matrix multiplication, these numbers will become 1. 1 multiplied 1 is 1, plus 1 into 1 is 2. 1 into 1 is 1, minus 1 is 0. So I'm left with 1, 0. And what is this? Get 0. So now if you want to program all of this on a computer, classical computer, your laptops or your desktops, this is how you would do it. And it makes calculations easier and fun. So let's take a 10-minute break and I'll introduce the first quantum algorithm. All right. So we're getting to the really interesting stuff now. Really interesting stuff. So my purpose in this course, in the first quarter of this course at least, is to introduce you to quantum computing, quantum communication, quantum non-locality and entanglement. And now we have all the bits and pieces together. We can start to kind of explain all of this. So the first thing I would like to introduce is I want to introduce a quantum algorithm. It's, I think, the simplest quantum algorithm, but probably the most used less as well, because if I want to do anything more complicated, you need to take my other course on quantum information processing. But even before I am able to introduce the quantum algorithm that I'm going to talk about, a little bit more about quantum gates. So quantum gates are really transformations. So what a transformation does, it's represented by an operator or a matrix that takes an input state psi and creates an output state. All right, these are matrices, these are column vectors. We've seen a NOT gate. Now when I draw diagrams of this kind, these are string diagrams, I'm taking motivation from circuits. You have wires and quantum information or quantum states flow on these wires. So this is a quantum channel and this is a quantum gate, a transformation. This could be, for example, a photon on a path, and this could be a mirror perhaps. This is a general generic language to describe quantum processes and quantum states. So we've seen a quantum NOT gate with a matrix. This is the matrix for the quantum NOT gate, isn't it? By the way, when I write matrices and when I write vectors, always am I presupposing a definition of the basis. I'm presupposing this all the time. I'm not going to mention this again and again. Sometimes this definition is called, if you want to remember this, the Zeeman basis. But I'm presupposing this definition of representing the basis vectors. So we've seen a Hadamard gate. U Hadamard. All right. But there are other kinds of gates as well. One gate that is really important is, and I'm going to introduce this gate because when I talk about the Schrodinger equation, and the practical example that I'm going to choose is a real quantum process that happens in the laboratory. I'm going to use this gate as an example. And this gate is called a rotation gate. Let's denote this by UR. So what this gate does is rotates quantum states in the quantum space. All right, let me give you an example. I'm going to write down the matrix for this gate a bit later, but let me first of all give you an example. By the way, before I'm able to move to the rotation gate, there is another kind of gate that you've already seen. In our beam splitter example, this was a quiz problem as well. This is my Mach-Zehnder interferometer. And what I did was, here I placed an element which is a phase element. What the phase element does is it's placed in the ket1 branch, so it does nothing to ket0, and if it's fed in with ket1, it just adds a phase factor to it. This is also a quantum gate, isn't it? So what should be the matrix for this gate? So how many elements will this matrix have? 4, a 2 by 2 matrix, because it acts on 2 by 1 column vectors. 2 by 2 matrix. So let's look at the first column. The first column is the output when you feed it with the first basis state. So when you feed it in with the first basis state, the output is ket 0. So what's the vectorial representation of ket 0? 1, 0. And when you feed it with the second kind of the basis state, the output is the basis state but with a phase factor appended to it. So what should I write here in the second column? 0. So this is the matrix for this element, and this element is called a phase gate, U phi, phase gate. All right. So by the way, now this is a physical picture, isn't it? It's a physical picture because this is talking about photons and paths of photons. I can convert it into the language of quantum circuits just by drawing boxes of this kind. And can anyone take a shot on how to do that? So if I were to draw a quantum circuit, a physical neutral kind of low level diagram for this physical implementation, I will have a quantum wire. First I have a Hadamard gate, then I have a NOT gate for the mirrors, then I have a phase gate, and then I have another Hadamard gate. So this is just a string of gates connected together. Now this language is independent of the physical implementation. Got it? Just a sequence of gates. And what I could actually do, I could look at the transformation of the quantum state in one go. If I have an input here, psi in, and an output here, ket psi out, I can look at the propagation of the state through this circuit, but I can take the matrices one by one and multiply them together. So first the matrix for the Hadamard gate. So psi in is acted upon by the Hadamard gate, UH, followed by the NOT gate, followed by the phase gate, followed by, oh sorry, this is a Hadamard gate, but followed by another Hadamard gate. This would be my output. Got it? I can multiply matrices together, can't I? All the matrices are of the same size, they're compatible for multiplication. This will give me my output. Homework problem, right? Now just look at the sequence of gates. So this is my time axis. Time flows from left to right. The quantum state comes in, sees a Hadamard gate, followed by a NOT gate, followed by a phase gate, followed by a Hadamard gate, and goes out. But mathematically the matrices come from right to left. This is the nature of this. If you want to find out the state here, that state would just be the result of this operation. If you would like to find out the state here, this would be the result of this operation. Alright, so this is a neat homework problem. So we've looked at kind of the NOT gate, we've looked at the Hadamard gate, we've looked at the phase gate, and all of these are single qubit gates so far. Now let's look at this rotation gate. What does the rotation gate look like? Now the rotation gate is, I want to first motivate it through a physical example that you're familiar with, and that's the polarization of a photon. So if I have a photon and I'm dealing with the polarization degree of freedom, suppose I input it with ket H. The photon is in a state ket H, and I have an element that rotates the polarization. All right. Yes, please.
Sir, would rotate mean के the
बता रहा हूँ, यही बता रहा हूँ. So the photon polarization comes in and is physically rotated through an angle theta. So it's not a polarizer, it's some other element, a polarization rotator, that converts this ket h into some cosine of theta ket h plus sine of theta ket v. All right. So if I want to draw this diagrammatically, this ket h can be represented by a circle. ये आवाज एक हल्की सी बोल लेने please. So this is ket h. This is horizontal polarization of the photon. What the rotating element or the rotator does, it takes this polarization and rotates it by theta. So this state, of course, this is my h axis, this is my v axis, is going to be cosine theta ket h plus sine theta ket v. This is the new quantum state. So what the rotator does, it takes any input state and moves it by theta degrees or theta radians from horizontal to vertical, which means in a kind of anti-clockwise direction. That's how we define this rotator. Yes, please?
So how would you represent this on a block sphere, which is 3D?
Well, I'm going to do that later. The next, I haven't talked about block spheres, but that's on my agenda. I'll do that. So this is what the rotator does to the input state. It just rotates the polarization. Different from a polarizer, by the way. The polarizer blocks anything that is not parallel to its optic axis. That's different. That's not a quantum gate. That's a strange kind of operation. All right. So if I were to write a matrix for this, this is my first input state ket h. Ket h and ket v are my two basis states. So what happens when I feed it in with the first basis state? I am able to now write the first column of this matrix. What is the first column going to look like? Cosine theta, sine theta. Now if this rotator is now fed in with the other basis state ket v, what output should emerge? Please say it again. So let's see. This is my input ket v, and after rotation this moves by theta degrees. Now if I look at this state, it's going to be, this is 90 degrees, so this is 90 plus theta. It's cosine of pi by 2 plus theta ket h plus sine of pi by 2 plus theta ket v. So this will become minus this will become sine of ket h, right? With the minus sine of theta ket h plus cosine theta ket v. So with ket h I have minus sine theta here, and with ket v I have cosine theta. Got it? So this is the matrix for a rotator. Matrix for a rotator. I can write this matrix over here. cosine theta, sin theta, minus sin theta, cosine theta. All right, so this is rotation by an angle theta. So now these are my 4 elements, 4 really basic kind of quantum gates. All right. By the way, if you look at these quantum gates, you take any of these matrices. These matrices have a property. The property is, the quantum states have a property, and that property is the normalization property. The matrices must also have a property, because the matrices cannot be just free floating, do whatever they kind, because if a matrix acts on a quantum state to give an output quantum state, if this is normalized, this must also be normalized, which means you cannot let the matrices to be of any arbitrary kind. There have to be certain constraints on the matrices as well, so that when they're fed in with normalized quantum states, they give normalized quantum states as the output. So if you look at all the matrices that I've written, if I were to take the complex conjugate of this matrix, which means it has elements, and I take the complex conjugate of each element, and then I write the transpose of this matrix, then this matrix, new matrix that is formed, let's give it the symbol U with this sign called dagger. Dagger. U dagger. U dagger means you take the complex conjugate and the transpose of the matrix in either order, doesn't matter. Then this U dagger is going to be the inverse of the matrix U. Homework problem, right? Let's do this as a homework problem for the phase gate and the rotation matrix. So all of these matrices that you've written, it's like slightly tongue twisting here. You take the matrix complex conjugate transpose, but that matrix that is formed is going to be the inverse of the original matrix, which means that if I were to take the dagger of the matrix and multiply it with the original matrix in either order, what should I get? Identity. So such a matrix U is called a unitary matrix. All of these U's are unitary matrices, and all of them, by the way, can be represented as rotation matrices, and I'm going to explain this when we talk about Bloch spheres. Anyway, all of these matrices, quantum logic gates, are unitary matrices. They preserve the normalization condition always. Now, equipped with this arsenal, any questions? Yes, please. So let's look at a matrix. Let's consider this matrix. Okay, my U of a phase gate, let's consider an example. My U of the phase gate is 1, 0, EI phi. Got it? So what's the inverse of this matrix? What's the inverse of this matrix? One, 0, 0, 1 over E I phi, which is E minus I phi, correct? So this is the inverse of this matrix. You multiply those matrices together, you'll get identity. Got it? Now let's find the dagger for this matrix. U dagger is also called the Hermitian adjoint. Anyway, so how do you find the dagger? You take the complex conjugate of each entry and transpose. It's a diagonal matrix, the transposition doesn't matter. So I'll get 1, 0, 0, E minus I phi. Is this the same as the inverse? Yes, it is. So take any matrix of the 4 kind that I've written, any unitary matrix, it will have this property. There was another question here. Do you get this point? Samajh aa gayi? No, what's your confusion?
I don't get the dagger. One is, I'm a little confused. I don't know what I don't get.
Do you know what the transpose of a matrix is? All right, so let me explain what is meant by transpose. I have a matrix A, B, C, D, 4 elements. It's a 2 by 2 matrix. Each of these elements could be a complex number. If I were to form the complex conjugate of this matrix, A star, that would mean A star, B star, C star, D star. So here I take the complex conjugate of this matrix and I get A star. Okay, this is how we define a complex conjugate of a matrix. The next step is to do transposition. What a transpose does, in English, transpose means left becomes right, right becomes left, something of that kind. So what this means is, now I take this matrix and form the transpose T. This symbol is T. And I can use one symbol for this complex conjugation and transposition, and that symbol is generally called A dagger. Now what I would like to do, I would like to take this matrix and convert these rows into columns, columns into rows. So this row becomes the first column. The first row becomes the first column. A star, B star, C star, D star. So this is what the Hermitian conjugate means, or the adjoint. This is the adjoint of the original matrix. All right, so far this is all that we need to know at this stage. Now what I would like to kind of propose, just to bring home this idea a bit further, let's talk about a really strange quantum effect before I move on to quantum algorithms, which owes its name to a Greek philosopher. No. Does anyone know who Zeno was and what his contributions were? Yes, please.
Zeno's paradox?
Yeah, what is the Zeno's paradox?
Oh yeah, it's
सुनो सारे.
basically वो टर्टल एक पॉइंट तक वॉक करना होता है, तो उसको कितने टाइम्स हम डिवाइड कर सकते हैं उसमें, वो infinitely amount of times divide कर सकते हैं, so the turtle would technically, according to that paradox, would never reach.
Right. It could be a turtle, it could be a shooter shooting an arrow and so on. So there's an effect which has been named after Zeno. It's called the Zeno's effect. So what this effect really is, I'm going to introduce this effect because it brings home some of these concepts really nicely. So let's talk about the Zeno's effect. In English, the Zeno's effect really means that a watched pot never boils. If you want to boil your egg, place it on a saucepan, just keep on waiting, it takes longer. So how does this contribute to quantum physics? So suppose I have an input quantum state psi which is ket h or ket 0, and I have a rotator which rotates through an angle theta, one of these rotators that I have over here. All right, and I have many of these rotators. A large number of these rotators. And I suppose that there are capital N rotators. And each of these thetas, all right, so forget about what theta is. So what would be the output quantum state? What would be my psi out look like? Each of these rotators does a theta rotation. So what would my output state look like? So you don't have to answer right now. I give you 2-3 minutes to think about it. Come up with an intelligent answer. नहीं समझ आई, सवाल नहीं समझ आया? So one rotator rotates through theta. This is the output state from a single rotator. Now I have n of these in tandem, one after the other. What should my output state look like? Can you please write down the output state on your notebooks?
N times u into qubit.
Very good. What's your name? Taha. Taha, can you please write down the output state for me? चलो ठीक है. Correct? This is what my output state is going to look like. So each rotator does a theta rotation. The second rotator does an overall rotation 2 theta. The third one 3 theta, 4 theta. N rotators back to back with nothing in between does n successive theta rotations. So my output state is going to be cosine of n theta ket h plus sine of n theta ket v. And you can also do the homework problem, use matrix notation to kind of solve this problem. Now if my theta is if my theta is 90 degrees divided by n, if my theta is 90 degrees divided by n, so there are n rotators and each rotator does a 90 by n rotation. What would be my final output state? Ket v. In that case, if I were to place a polarizer here, which is horizontally aligned, and I place a detector here, what's the probability that this detector clicks? 0. Because my output is now exclusively V here. It's exclusively V. All of my cat H has been rotated in successive steps all the way up to cat V. And at the final, I'm doing a measurement on cat H. And the overlap of cat V with cat H, of course, is 0. So the probability that this detector clicks is 0. Alright, so what's happening is that a succession of rotation gates has transformed the input quantum state from horizontal to vertical. Now comes in the Zeno effect. The Zeno effect means, now what I would like to do is I have the same setup. N of these, each rotation is pi by 2n. All of these are rotators. And the state has evolved. Now what I would like to do is, in between these rotators, in between the rotators, I place horizontal polarizers. Will the detector click? Two and pi by 2 is 90 degrees, right? 90 degrees divided by n. Input is still cat H. The input is still cat H. The first question is, will the detector click? Yes. No, yes. It's going to click. And it's going to click with a very high probability. The reason is that each of these polarizers is doing a measurement. So consider what happens here. Here a new state is created. It's in fact a rotated state, cosine theta cat H plus sine theta cat V. Now this photon, remember these are single photons, this photon sees a horizontal polarizer. So it's absorbed with some probability, it annihilates, it just vanishes with some probability and emerges with some probability. What's the probability that it emerges? It survives this scathing attack of the polarizer. What's the probability that it's preserved? Cos square theta. With the probability cos square theta, it goes on. Now if this n is really large, then this angle is small. So with a very high probability, which is cosine square of this theta, it emerges. It keeps on going. Then with the probability, an additional probability cosine square theta, it emerges from here. It has been converted, if it emerges, it's now in the state cat H, because it's parallel to this optic axis. So all the time this polarizer is projecting the quantum state back onto the horizontal axis. And a new state is being created with cat H. So it's rotated here, but if the photon emerges, it's in the state cat H. Here it's in the state cat H, cat H, cat H, cat H, all the way up to this point, it's going to be in a state If the photon emerges and it's detected, it's going to be in the horizontally polarized state. The photon's evolution from the horizontal to vertical has been arrested. It has been impeded. Usko rok diya gaya by this act of successive measurements. So you keep on looking at things, you can kind of arrest the progression of quantum states. A watch pot never boils. You keep on measuring things, it goes back to its initial state and its evolution. No matter how many rotators you use, the state does not rotate. By the way, is this probability that this detector clicks, is it high or low? High. Why is it high? Because cosine theta for theta small is very close to 1. If you take cosine theta and square it, if theta is small, which it is because you have a large number of rotators, each theta is small. So if you say have 90 rotators, then each rotator has a 1 degree rotation. 90 divided by 90, 1 degree rotation. It's small. So you take cosine of 1 degree, which is a number really close to 1, and then take the square of it. So what's the overall probability that this detector clicks?
Close to 1.
Close to 1, but what is it exactly? Cos square? Exactly, cos square n times. The probability that this detector clicks is cos square theta n times. It's cosine of 2n, cosine theta raised to power 2n. And there's going to be an advanced homework problem, Salman. If you're familiar with the Taylor expansion or the Maclaurin series, we can give this as a homework problem. This is very close to 1. It's really, really close to 1. Yes, please. So take kind of. So this is the series expansion, and you can have higher order terms. So if this n is large, this is what it asymptotes to. You can do a numerical calculation and find out what this is. By the way, not time to go. Abhi waqt nahi aaya. I want to ask you a question here. Can we say that this is an interaction-free measurement? The polarization of a photon. If you have no polarizers, this detector never clicks. But now polarizer works by blocking light. Now you are inserting polarizers which tend to block the light, but the probability of detection goes up. So if the detector clicks, it means that the photon has passed through the polarizers. It has seen this object. It has interacted with the object, because the object, which is the polarizer, has created a new quantum state. So inevitably, the photon must have interacted with the polarizers in order to create the quantum state ket H, yet it has not been absorbed. So this is also an example of an interaction-free measurement. Or any questions about this? We'll now discuss our first quantum algorithm in the next class, inshallah.